let's start today's topic, and today's lecture will be about strings and automata. So, some of you might have heard about some of these topics on your maybe algorithm and data structures classes, or maybe formal languages classes. We will try to summarize what we use from these topics in programming competition, and we will try to see most useful algorithms that are there, how can we use them to work. So, we will start with some definition from the formal languages class, which is DFA, deterministic finite automaton. Who knows what is that? Oh, not so many people, just approximately 1,000. Okay, let me ask you. I'm sorry, I should have done this yesterday, but let me ask now. Who is on his first year of study in the university? Are there anybody? Okay, there are some people. Second year? Third year? Fourth or more? Okay, so most of you are at the I don't know, greater years of studies, so you should know many things. Okay, so what is deterministic? From our point of view, it would be a graph, a directed graph. I would not say multigraph, and its edges are marked with characters from some alphabet. So we have like the vertices of this graph are called states, and the edges of this graph are called transitions. So we have like this visual, but there is also another additional constraint. From each state there should be a transition by each character. So here we can guess that there are two characters at all, A and B. And so on this state I have the transition on A, we should also put a transition on B, for example. From this state I have already drawn the transition for B. We can draw, for example, the same transition for A. For this state, we should also have both transitions. For example, we can draw provinces. And for this state, for example, we might decide we don't need the transition for A. How can we deal with that? We usually create special vertex, a sync vertex, it's called. So we can move all unnecessary transitions to that sync vertex, and if you go there, you travel, so you cannot do anything useful anymore. So again, the finite automaton is the graph with the directed edges. For every edge, we have a letter, a character written on the edge, and for every vertex, which are called states, we have exactly one transition for every character. One of the states is called the initial state, or the starting state, and some of the states are called final or terminal states. So the idea is the following: when you have some text, not so very text like this, you go to your automaton starting from the initial state and follow the transitions corresponding to the letters. So here you go, like A, B, A again, and we are here in our sync state, and again A, B, B, so we just B, B, and we are. So let's take another text, for example, B, B, A, B, B, A. If we do this, we start here, B, B, A, B, B, A. And we end in the terminal state. If we end up in the terminal state, then this world is accepted. And if we end up in the non-terminal state, which includes the sync state, then this word is rejected. So this is finite automatons. They have a lot of uses actually in computer science, and in competitive programming there are usually several topics that finite automatons help you. One is string algorithm. There are a few string algorithms that using finite automatons. One of them is the algorithm that you probably know without any automatons, which is substring search using prefix function, or yes, prefix function. It's called sometimes KMP algorithm, or extract algorithm, or prefix function. This can be reformulated to be using automatons, which we will do in a couple of minutes. The second algorithm, which is actually the generalization of this algorithm, is apophorosic algorithm, which is essentially the same algorithm as KMP, but for many stuff. The third algorithm is suffix automaton, which also solves some string matching problem, but it has a different setup. In these two setups, you have initially the patterns, and you can process them if you need, and then you have the text for which you are making the substring search. You're solving the substring search problem. And for the suffix automaton, you have the reverse. You have the text, you process the text, and then you can get patterns, and you can process patterns, search them in the queue. The second thing where automatons are used is regular expression. Regular expressions are widely used in like gradient system courses or something like that. In other matching tasks, what we will see is how to process regular expressions and convert them to finite automaton. So we can match regular expressions, compare regular expressions, do other algorithmic tasks on regular expressions. So that will be our plan for today. It will not be in exactly this order, actually. We will actually start from regular expressions, because it gives us a lot of some theoretical knowledge and also algorithms for automatons that we will later use for problems. So, okay, let's go with that. Well, to start with something interesting, let's start with automatons and regular expression. What is a regular expression? There are actually two types of regular expressions. One is so-called academic regular expressions, and the other is like I don't know, the adjective like formal, I don't know, usual operating system, Linux, Perl, regular expressions. Let's call them Perl. Because they were the first appeared, maybe not first, but widely appeared in the programming language Perl. You know this language? I guess you know. So, academic, we will work with academic regular expression. What is an academic regular expression? We have, again, some characters, in this example, A and B, and we are working with so-called languages. Language is the set of strings. I write it like this, but you must understand that if you write it like this, the set in C++ is just a finite set, so you have like some finite number like 10, 100, 1 million strings, but language can be infinite, so you can have infinitely many strings in this language. So let us form some set of languages. We will start with the very basic languages. First is empty language. Set can be empty, so there are no words in this language. The second, easiest if you can arrange them by easiness, language would be the language that contains exactly this set, yeah? It contains exactly one string, and that string is an empty string. We know this as epsilon. The third one is, not the third one, but the next series, if we go by gradually increasing the complexity of our language, there will be languages that contain one word that consists of one letter. So if we have two letters, A and B, that is the language A and B. So these are called regular languages of zeroth generation, or the basic regular language. And then we have three operations that are called regular operations. The first operation is union. It is denoted, usually you denote the union of sets as sort of half character, yes, but in regular expressions we will use the vertical part. The next is concatenation. The concatenation is as usually denoted as nothing, so you just write the strings that you want to concatenate one after another. And the third is called the clean start. And it's denoted as start. And so what is the idea of these operations? The union is when you take two sets and you unite them together. The concatenation of languages works like this. If you have two sets, A and B, their concatenation is concatenation of every pair, the word from the first set and the word from the second set. For example, A concatenated with, say, A and B, that would be. It's not necessarily like A and AB concatenated with A, B. So we concatenate every pair, A and A is A and B is AB, AB and A is again AB, but since this set doesn't have multiple appearances of the same string, so we write it once. And AB and BA is AB, BA. So in the clean start is the following. So we take some language A, we want to apply the clean start, and it is also the test of closure. So and we say that A star. Well, I will write down and then explain A0 or A1 or A2 or so on until infinity. So we make the zeroth power, the first power, the second power of the language and so on. What is the power of the language? We have kind of multiplication, which is concatenation. And so what do? We multiply or concatenate the language with itself as many times as we like and unite all the results. So in this case, it's clear what is united once, 2 times, 3 times, and so on. The only question is what is unite, what is the concatenate the language with itself 0 times. Yes, so there are intuitively two options, like empty language or language with a the epsilon language, and the epsilon language is better because we would naturally like that if we concatenate the zeros power to whatever other language, we get the same thing. It's like 1. And epsilon is exactly does exactly this. When we concatenate it with anything, we get the same. So, for example, if we take A, B, and apply the cleanser, we get what? We get the set of strings, and this is where the word set goes away from C++ to some mathematical meaning of the word set. Here we have the words from A and B that can be represented as the concatenation of an arbitrary number of these two words, so A and AB. That can be reformulated in this particular case with the simpler words, so that there is AB for any B. Exactly this set of words. It can sound more complicated. And so what we say is that the regular language are the languages that can be obtained from these initial languages using this three operations. Okay? Does it match with what your professor told you in your university? Okay. So what do we do now? Actually, we will sketch the proof. We will give more details to algorithms to be beyond this proof than to the mathematical proof. That actually for every regular language there is a DFA. And as I told you, we will try not to prove it just to prove, but we will give the algorithm that. Why would we do that? Because this algorithm actually consists of 3 stages, and 2 of these stages have the value by themselves. And the whole algorithm is also nice because it allows you to solve some problems. Well, not that there were so very many actually problems of this kind at the programming contest, but I think about a dozen of the years there were. And sometimes you can also see the finito automaton in such setting that you are given some graph with colored edges, and you need to do something, and there is some constraint on those colors. And if you rephrase the colors with the letters, you often get exactly the concept of the finito. Okay? So let's go. As I told you, the path will be quite long. So we will start with going from regular languages to so-called epsilon NFA. Whatever it means, you do. Well, if you had the good classes of formal languages, you might have heard that. From that, we will go to NFA. And from that, we will go to DFA. And well, this step is not so valuable for me, but these 2 steps are actually quite nice. Let's see. So what is NFA? Let's discuss first. When we were discussing DFA, we said that for every state there should be a transition, exactly one transition with every character. What if we don't use this constraint? Let's try right here and see what it shows. For example, let's so bad. Okay, so let's for example see the following output. 5 states. So it will be A and B here. This will be the initial state. A, B, and this will be the terminal state. So what is So what is the idea of this autonomous? Okay, what is the idea of this automaton? It is not the DFA. It is not DFA because there are problems for some states. For example, for this state there is no transitional name, no transitional B, no transitional name, and no transitions at all. But this problem of these four states, we know how to solve easily with this sync state. So we just add the sync state and move the transition. But for this state, there is a more fundamental problem. It has two transitions on A. You can go forward or you can stay. And that problem cannot be easily solved with like drawing additional transition. We need to get rid of one of the transitions which we don't know how to do. So this is called NFA. But how does it work? When you have some string like does it accept it or not? The idea is the following. The NFA accepts the string if there is some path marked by these letters in this order that leads to a terminal state. So when you have the choice, if there is at least one choice that leads to acceptance, then you accept. If all the possible choices lead to non-acceptance state, then you do not accept. So let's first look at this string. So here we have two options on the very first letter. Either go forward or stay. If we go forward, A, B, everything seems fine, but we have nowhere to go then. So we die, yeah. So we don't have any further transitions. We cannot end up in the terminal state, so we are stuck here. The next solution is to start from staying. Okay, we stay A, then B, we have no options, we stay. A, again, there are two options, stay or go forward. This, now we already know that A, B, and B is a group string, so we go forward, and A, B, we accept. So there is a way to accept that, this one, and we accept. If we take some other thing, for example, A, B, then there is no way, it's quite clear that there is no way to accept this string. If we start with this and go A, B, way to go to B. If we go forward immediately, A, B, again, everything seems so good here, but no. In the end, we do not accept. So this is NFA. In general, if you study computer science, you might have heard about non-deterministic things, not only in the context of automatons, but also in the context of programming, in the context of Turing machine, in the context of NP, non-deterministic polynomial time complexity class. Is there anybody who is at this stage of studying who have had classes about NP, for example? Oh, great. I like here because I teach complexity actually at my university, so this is my favorite topic. Okay, cheers to you, but let's get back to our topics. Well, this NFA, actually, can you describe what it accepts in simple words? Well, any combination of A and B followed by this string AB. Yes, that's correct. So, in other words, any string that ends with AB. We will get back to it when we are moving when we move to the second part of our lecture actually today, because this automaton can be its deterministic analog can be used for string matching, but now our goal is another. Let's see if there is some non-deterministic automaton. Can we make it deterministic? So can we do this? Well, the spoiler answer is yes, of course we can. how do we do that? Let's try to do the following. Let's create a matching algorithm. The matching algorithm is you have the automaton and you want to answer the question, can you accept the word? Can this automaton accept the word? Since for DFA, it is very easy because you have only one transition for the first, so you just follow this transition, and in the end you check if you are in the terminal state. But for NFA, you have choices, and you want to await vector. But of course, it's easy. It's like simple dynamic programming solutions. So let's see, can I U is can we be in the state U after I transition? That's true or false. And it's easy to update, so it's like for V in transitions from U by the character Si, so it is S I plus 1 V is, yes. Do you agree? So it's easy dynamic programming solution. That is one transition, and if we can be at the state U after I steps, then after I plus 1 steps we can be in every state V, so that we can follow from that step. So for example, let's take this string and this automaton. So we have like, yes, okay, I think that it's easy enough not to show in the example. Yes? Question? Of course, if can you like I omitted all fors and ifs, but if you hear that if you for I from 0 to len of s minus 1, for u from 0 to n minus 1, if for. Okay? I just wanted to give you the core of the presentation, but this stuff I thought it was always. Okay. Now, let's look at this closer. So, for example, so it's if I have I, U, so like after 4 steps, where can we be? So can we be in the state 0 after steps A, B, and B? Of course, we can always be in the state 0. That's no problem. Can we be in the state 1? I guess no, because it ends with B and we count here by 8. Can we be in state 2? I guess yes. Stay, go forward, go forward. Can we be in the state 3? No again. Can we be in the state 4? Yes, go forward, forward, forward. So this is the one line of this dynamic programming for I equal to 4 and for all. So since our array only contains zeros and ones, like true and false, this can be seen as a bit mask. And this exactly this mask, I don't know, 1 plus 4 plus 16, like maybe 21. So we can use bit compression and say that can I is now in or long or whatever. It contains a bit mask, bit set, yeah, and it was a bit mask, bit set of which states can we be after I step. And there are actually two n possible bit masks. So now, as we can see, this transition only depends on the character Si, on the i's position of the string S, and on the if can IU, on the bit mask of can I. So actually we can create like the recalculation. We can make for every character. We can make for every bit mask. To calculate which will be the bit, if the ith mask is mask, which will be the I plus first mask. Okay. Mask. Next. So if we store that, we get like the array goal from mask by C is mask. And what we get is that actually now we are starting with the mask that has one bit set in the initial state. And then after each transition we get the new mask that only depends on the character that we are using. So this is actually exactly the DFA with the states being masks. And the transitions calculated with this breakout. The only bad thing in this automaton is what? The number of states. Yes, it has potentially too many states, exponentially many states. In the real applications, like for example, if we try to apply this to this automaton, it has like 5 states. So the potential is that the deterministic analog would have 32 states. A little bit too much, too many. But actually, if you, not all masks are possible. For example, in this case, is this mask of all ones possible? Of course no, because you cannot simultaneously be able to be in the state 1 and the state 2, because this means that the last character was A, and that means that the last character was B. So there are many masks that are impossible to reach, so you could optimize your solution, optimize your algorithm, but by only adding to the set of states of your deterministic analog of this automaton, those masks that are reachable from the initial mask, which is all zeros and one at the starting state of the initial state. So unfortunately, in general, it doesn't work. So there are indeterministic, non-deterministic automata such that equivalent deterministic automata has exponential number of states. You can, if you didn't do that in your formal languages class, you can do this, the automaton is the following. A, B, A, if you make it like this and extend it there, the equivalent deterministic automaton is easy to show, but it show would have exponential number of states. There is no way to make it small. But for this, for example, the equivalent deterministic automaton has the same number of states. There are only 5 possible masks original, and this is actually the indeterministic KMP automaton, which we will consider a little bit later today. So okay, we know how to do this. Now, what is epsilon NFA? Epsilon NFA is similar to NFA, but it also allows transitions not marked by any letter. These are not wildcard transitions, but these are empty transitions. Like you can go by this, but do not skip any characters on your string. So let's have another example. For example, For example, let's take a look at this automaton. So I marked empty transitions with epsilon, which we usually do, because if we don't, there is always misunderstanding. Did we forget to put the character there, or is it an empty transition? So we use epsilon for that, and that is why it's called epsilon NFA. So the answer, what is the answer? What does this automaton accept?
Any number of A's followed by any number of B's followed by any number of A's?
Yes, well, any number of A's followed by any number of B's followed by any number of A's. By the way, if we use our regular expressions, notations, we can say like any number of A's is clearly A star, any number of B's is clearly B star, and any number of A's again is A star again. So this is this can be denoted with this regular expression. So this is called epsilon NFA, and we can actually get rid of epsilons using quite simple algorithm. Let's describe it briefly. There are 3 steps that I will show on this example. The first step is let's make so-called epsilon closure. It's similar to transitive closure. Take epsilon transitions, run Floyd-Warshall algorithm on them. Do you know Floyd-Warshall algorithm? Yes, and add all the new, if there is a path, add an edge. So in general case, you can get a little bit more epsilon transitions. The result in automaton clearly does the same thing, because if you can go by the new edge, you could always go by the older edges, because they are just epsilon, so you don't need anything from the input. And now you can never make 2 epsilon transitions in a row. Always make at most 1 epsilon transition, and then you should always make non-epsilon. Okay, then, for every possible epsilon transition, and then, oh no, the second step is, if you can go by to the terminal state by the epsilon transition, mark the source state of that edge as terminal as well. Second step, and the third step is, so again, clearly that doesn't change what the automaton do, because if you could get to this state, you could always get to the terminal state by working by epsilon transition, so you should accept it. And the final, third step is, no, almost final, okay? If you do this, no, what do we have after this? After this, we should never use the epsilon transition as the last one. So we at most 1 epsilon transition in a row, and the epsilon transition is never the last one. Then we take epsilon transition plus non-epsilon transition and compact them into non-epsilon transition. So for each section case, epsilon plus b, we add bh. Epsilon plus a, we add dh. Epsilon plus a, we add dh. So for every combination epsilon plus non-epsilon, we add the non-epsilon edge shortcut. Well, now epsilon transitions are redundant, we don't need them anymore, so we can just remove all of them at once to get the equivalent automaton. It sometimes looks less clear. For example, here we get this. It's again the any number of A's followed by any number of B's followed by any number of A's, but this time it is not so absolutely clear as it was previously, although of course this is such simple that it can be easily deduced. But in more complicated cases, epsilon transitions help you to be sure that what you do is correct. Okay? Now the final third, which is actually for this part the first step. Let's see. So, what we said, we start with our basic regular languages, use 3 operations, union, concatenation, and list star, and we get some other languages. For every such language, we can easily create that string that describes it. For example, we can say that we did it here. We said take A, apply to instruct. Take B, apply to instruct. Okay? What does it mean take A? Take this basic language. So we could, for example, here, we could write it in another way. We wrote it like this, but AB is not the basic language. It doesn't appear here. How can we create it from basic languages? Take A, also take A and concatenate it with B, unite them, and then apply the construct. So this is called academic regular expressions. The real-life regular expressions, like in Perl or in the Linux, they have more options. Some of them are just syntax sugar. Some of them are actually changing the power, like back references. They are changing the power of regular expressions, making them non-academic. But that's not important for us today. So why we have such a regular expression? I use parentheses because it is the priority of the operation. This is the lowest priority, this is the highest priority, this is average priority. So this is the agreement that we use brackets to change the priority, as we usually do in arithmetic. So here we have some regular expression. We can create the epsilon and FA for that using the following recursive algorithm. So if you have the basic language, there are simple automatons that correspond to this basic language. For the empty language, we have initial state and terminal state, and they are not connected, so no word is accepted. Okay, we could make it's not what I am creating is not, of course, the unique automaton for every of these languages. There can be other options, but we will create something that will work for us. So for the epsilon language, the same, but now we connect that with epsilon h. And for the one-word languages of one character, again, we connect them by the h, but marked by the transition, but marked by the corresponding character. So this is the basis, and now we can make the operations. For the union operation, we have like A, and we have B. Let's make additional condition, let's add additional constraint that is satisfied for these basic automatons. One initial state and one terminal state. It is easy to do for non-deterministic automatons. For deterministic it is not always possible, for non-deterministic it's easy to do. So here is initial, here is from the terminal. How do we use our tools for non-deterministic epsilon automatons? To make choice, A or B. Yes, we make like this, epsilon here, and we have two terminal transitions. That is not a problem in general, but for our recursive setup, it is better to create one terminal. So we have this, and we have the terminalness of that, of those things. Okay, so this is union, the concatenation. Now that we see the general idea, it is very easy to create also concatenation between stars. Concatenation goes like this. And the clean star what would you do with clean star?
A loop back with the
A loop back is a good idea, but if we then, well, okay, generally if we do it like this and then like this, here we can just make a loop back. It's okay. But for the general setup, for more safety. Oh no, loop back is a. Let me explain you. Loop back is not okay. So if we make a loop back in this step and do not add anything new, then you are making it 1 or more. You need a 0 or more. But if you make a terminal, you make it incorrect because you might have passed through initial state, not only in the end and in the beginning, but also at some other point, and that would add potentially some incorrect words to the set of accepted. So, to make it more safe, let's not get inside automata, but let's walk around outside of it. So here, you can do this, and you can do this any number of times you like. That is not the optimal construction, maybe, but this is safe. So using these 3 options, we can recursively build the epsilon FA for any regular expressions. After that, you can process back. You just have the regular expression, you parse it, or maybe you don't have it as your input. Is actually not so very often that you have some regular expression as input. It generally appears to you when you're considering some written text in the statement of your problem, so you think this description matches this regular expression, I create this. After that, you, depending on the task, you can make 0, 1 or more, or 2, or further transitions, and stop at the point where you can do what you like. We'll make a side note that actually you can go back as well. For every DFA, you can create a regular expression that corresponds to the number, to the sets of strings that it accepts. But we would not get into that because we're not at the formal languages class. So this is, I don't think that this is useful for the context. But if you wish, you can easily find this. The whole cycle is called clean 0. So we can easily Google that. Okay, so what now we get from regular expression to DFA. Now what could we do with DFA? First of all, DFA has several nice properties. First of all, it's graph. So since it's graph, you can use graph algorithms on that. DFS, I don't know. Check for if it's a cycle, acyclic. Find its strongly connected components and make some conclusions from those. So you get a complete, if you have a regular expression like this, or like this, and you are asked, for example, to count the number of words of length n that match this regular expression. Okay, you can create kind of parse tree for this regular expression and try to make dynamic on the tree. But it would be difficult actually to avoid counting the same thing multiple times. Because especially when stars are involved, it's quite difficult to make unique matches. So very often the same string matches multiple ways to the regular expression, and For example, here this A can be included into this A and so on. After you do this and you get this automaton, you can solve the problem how many paths of length n lead from this vertex to the terminal. This can be kind of this can be solved using some algorithm similar to Bellman-Ford algorithm, this dynamic programming, how many words of length L go from the vertex initial vertex to the vertex. Then, if n is big, you can use matrix multiplication to speed up your calculations in a similar way to counting the number of paths generated. Yeah? So this opens you the number of graph algorithms. For example, what is the shortest string that matches this regular expression? Again, avoiding dealing with the path tree, you create the automaton, and you can find the shortest path from S to the set of terminal vertices using, for example, BFS. Another thing that you can do with the finite automatons is the product of the automatons. This can be applied to both deterministic and non-deterministic automatons. What is the problem with deterministic automatons? It is very good. The very important feature of this again is that every string matches in a unique way to the DFA, and that allows you to count something. But if you don't need to count, then maybe it's not so important for you that the string matches in the unique way. Then you can skip the last step that I have erased from here, skip the last step of determinizing your automaton, and work with non-deterministic automatons. For example, BFS can be applied to NFA as well. You can find the shortest string that matches regular expression using this NFA, not necessarily DFA. So the product of automatons corresponds to analyzing several properties at once. For example, you might have two properties set up by finite automatons. Let's see an example. The first property would be the number of A's is divisible by 3. So let's create the automaton for the strings that match the condition of number of A's is divisible by 3. The state would correspond to the remainder of the number of A's by 3. So initially it's 0, if we get A it's 1, if we get A it's 2, if we get another A it's 0 again because it's modulo 3, and the B's, they don't change this, and this is the terminal state. You might notice that initial and terminal is the same. The second option, let's take this one from this. So the string ends with AB, AB. So let's draw it like on the Cartesian plane. That's like x axis, and left would be our y axis. So like A and B allow us to keep A, B, A, B. So what is the product of the nodes? Let's consider that now we want to keep track of both these options at once. Then our state would be what the pair. Which state are we in the first automaton, and which state are we at the second? So the resultant automaton has the product of the states. So in this example, this would be 15. I will not draw it completely, but I will start to get the essence of how the transitions So for example, let's make the transition from A from this by A from this vertex, from this state. So in this automaton we can stay in the same row or go to the next row. In this automaton we always go to the next column. So we have two transitions. Stay, next row, and always next column. For B, here we always stay, and here we always stay. So here we also always stay. And so on. So here again, A, B. Here again, A for A, and so on. So for each state, we consider, and for each character, we consider all options for the horizontal automaton, so-called, yeah, for the first one and for the second one. And for each pair, we make both moves. They are independent, yeah. So we have separately we have column, separately we have row. Actually, the thing that we are multiplying two automatons is not important, as you can clearly see. We can make a three-dimensional, four-dimensional automaton and so on. It's just more difficult to draw, but inside your computer it's not a problem. So now, what about the initial state? The initial state is clear. Initially, we are in the initial state in the first automaton, and then the initial state in the second automaton. And for the final state, that depends on what we want to check. As I said, we keep track of both automatons, what is going on there and what is going on there, but what do we want to get? One example, we could get and of these conditions, the conjunction of this condition. We get this and this. In this case, we mark as terminal this exactly states which are terminal in the terminal column and in the terminal row. We could make OR of these things. For OR, we can have other option. We can make like we did for regular expressions. We can add epsilon transitions. We can put it side by side, make epsilon transitions to choose this one or this one. There is another option for O, which is actually better for DFAs, because if it's NFA, one of those is NFA, then option put them side by side is better, because this time you get n times m states, and if you put them side by side, you get n plus maybe 2 states. But if they are deterministic and you want to keep them deterministic, then in this case you keep them deterministic. But in this case, you go to non-deterministic, and after determinization, you can actually get up to 2 to m plus n plus 2, which is a lot better, a lot worse than m times m. So there's kind of trade-off if you want to keep determinism. So saying here for OR condition, we can mark the states that are in a terminal column or in a terminal row, and it's clear that any Boolean function can be implemented like this for any number of conditions. So we can take 3 conditions and like median, at least 2 are satisfied, you can create that. That actually means that any Boolean expressions on regular conditions, the condition which can be specified by regular expression, yeah? So any Boolean expression on regular conditions is again a regular condition with many factors, because it can be set up by next thing that we can use for DFAs is the analysis of regular expressions. For example, if they are intersections. So is there any word that matches both regular expressions? Now we know that it is easy to do. We just create the product. Well, easy to say, not so easy to do, because actually the code for all these algorithms are simple and short in code, but there are many of them. But generally, you just create the automaton for both of the expressions. You do not need determinism here, so you can omit the last step, the exponential step, create two NFAs, take the product and use, for example, GFS to check if there is a path from the initial state to a terminal. If there is, then the regular expressions intersect. If there is none, then they do not intersect. The last thing before the break, before the coffee break, we will consider the problem of equivalence. We would like to check if two regular expressions are equivalent. For example, there can be easily looking, but non-trivial for some algorithmic analysis at first sight cases. For example, A or B. Star is the regular expression that matches any string of A's and B's. There are some other options for that. For example, like A or B, star concatenated with B or A, star, and that is all star. Well, at first sight, it looks like there should go patterns of odd or even number of A's or B's, but actually no. Star can evaluate to 0 repetition, so you can take A's from here, B's from here, and connect them in any order, and you will get any string. You can get any string, and also in multiple possibilities. So checking equivalence of regular expressions is non-trivially looking for regular expressions themselves. If we move from regular expressions to automatons, then this problem can be solved. The good news, the bad news, only for deterministic automatons. For non-deterministic, the problem is hard. I don't remember exactly the complexity, maybe even space hard. Let's see. For deterministic automatons, actually, what you can do is you can do minimization. Minimization is the algorithm that creates the equivalent deterministic automaton with a minimal number of states. There are multiple algorithms. There are several algorithms with a square complexity to the number of states, and if n is the number of states, n square is there. And there are algorithms with n log n complexity that are actually tricky to write. I remember a couple of years ago, like 15, I was participating in some camp already at the college, but I was solving the contest just for fun with the team of other coaches, and we had the problem of minimizing automaton of 50,000 states. So n squared was not an option, and I knew I teach an algorithm at the university, so I said, I told my teammates, okay, we are safe. I know this algorithm, I'm teaching it, and I tried to learn. Actually, it took like 2 hours, and it still didn't work. Teaching something doesn't necessarily mean you can do that by yourself. I don't know, and we got wrong answer, by the way, not time limit. There are some tricky places where you can get time limit, and I knew them, and I tried to avoid them, but maybe too hard. Okay, so we will start with the squared algorithm, and then we'll give you the sketch, the idea how to move from that to algorithm L, but we will not get into details here. Okay, so the main idea is, let's look at the following automaton, for example. The words that contain the even number of A's. So again, A's and B's, but now we want it not divisible by 3, but even simpler condition, even number. One option is to make a similar automaton only count A's. The other option is, if we are not so very optimizing inside our brain, we could count A's and B's, for example. So we can say number of A's is even odd, number of B's is even odd. So A goes like this, and B goes like this. For example, initially we thought that we would need to count the number of B's as well, for some reason. But then it turned out that we don't need to do that, but we kept counting them, not to refactor the whole. So these two automatons are equivalent. They are both accepting words that have the same, the even number of A's. But they are different, they are not isomorphic. This has 2 states, that has 4 states. And all states here are reachable, there are no redundant states. So what do we need to do? We want to find equivalent states. What does it mean, equivalent? Equivalent means that if we are in one of the states, we cannot tell in which one by only following the letters and checking if we are in the terminal condition. So formally, we say that we will go from non-equivalent. So we say that U is not equivalent to V, can be told from B, not equivalent to V. It is not equivalent to V. If there is S, string S, so that we start from U, get by the string S and go to the terminal state, and if we start from V, we go by S and get to the non-terminal state. That's non-terminal. Or the opposite. So the terminals, the condition of these states being terminal is different. So this or the reverse. These are called non-equivalent, and they are differentiated by the string S. And if 2 states cannot be differentiated by any string, they are called equivalent. If there are 2 equivalent states, we can remove one of them and move all transitions to the other. For example, here, let's see, these 2 states, in a sense of our algorithm, of our task, are equivalent because whichever string we take from this state, if it contains odd number of A's, we get to the terminal state. From this state and from this state also. If it contains even number of A's, we get to the non-terminal state, From this as well. So these states are equivalent, and we can get rid of one of the states, for example, from this one, and move, outgoing transitions are gone, and incoming transitions are moving to the other equivalent states. This goes back. Why is it possible? Because if we track the string, it doesn't matter to which of the equivalent states we get. Whatever follows, we will, in both cases, either end up in the terminal state or end up in the non. Okay, now, how can we find this? We will find non-equivalent states, and this will help us find equivalent. All the other pairs are equivalent. How can we find non-equivalent states? There are pairs of definitely non-equivalent states. Which pairs do you think are such? Yes, one terminal, one non-terminal are definitely not equivalent. They are differentiated by the empty string. Now, we'll make like BFS. We put pairs of non-equivalent states into the queue. So if we pick the non-equivalent states, U and V, that means that, let's reuse this picture. That means that we have some string, it doesn't matter which one, that leads to states of different terminal condition, different terminality. So how can we add up? How can we find new pairs? Let's look for longer strings that differentiate some states. Let's iterate over all possible characters and see if we get from x to u by this character c, and from y to p by this character c, and then x and y are differentiated by cs. So if we don't yet know that they're non-equivalent, we can mark them as non-equivalent and put this pair into our Q. So since each pair can only get into the Q once, we get at most n square pop and or push operations for our Q. And this iteration over characters actually takes sum for all C, sum for all U, sum for all V, incoming degree by C to U multiplied by incoming degree by C to V. We iterate, that is the upper bound, we iterate over all incoming. We iterate over all incoming edges from to U, and then iterate over all incoming edges from V. This can be moved here, and the sum of all incoming degrees is equal to the sum of all outcoming degrees, because each edge has both the start and the end. And the sum of all outcoming degrees is n, because there is only one edge for every character outgoing. So this is n times n squared times the number of characters, which the number of characters is usually considered a constant, so it is n squared. So this is BFS, you can run it, you get all non-equivalent pairs, and all others are equivalent, so for every equivalent pair, for every equivalent, even every class of equivalents, you keep only one vertex, one state, and move all edges that go each other into that one, and then you remove all the non-equivalent ones, so you get only one. You get only one option. After that, after you minimize, it can easily be shown. Let's not do this now. You can easily do it as an exercise that the minimal automaton is unique. So you cannot have two. If two automatons have the same number of states and do the same thing, so they are the same number of strings, the same set of strings that leads to terminal states, then they are isomorphic in a sense of automatons. So you can make a bijection between the states and the transitions are between the corresponding states. It's quite clear. So now, when you want to check equivalence of two automatons, you minimize them and check if the results are isomorphic. And you can, there's a question, please.
To check isomorphism, can you just map the initial state of the first automaton to the initial?
Yes, let's describe how to check isomorphism for the automatons. You know that isomorphism for graphs is difficult, if nobody knows how to solve that. But for automatons, we have one great benefit. The edges are already marked, which one corresponds to which one. So you start by matching the starting vertices, and then the letters on the edges tell us what to match next. So for automatons, checking isomorphism is easy, unlike general graphs, when the main problem is which edge corresponds to which edge for the outgoing edges. So if you check for equivalence, if you know how to check for equivalence, then you can check for other theoretic properties. For example, A subset of B is formulated as A intersected by B is equal to A. Intersect we can do with the product construction. Equal we can do with the equivalence that I just learned. And similar, if you can rewrite using Boolean operations and equality, then you can check this condition. So, a side note from the theoretical computer science, as we can see, analyzing academic regular languages is easy in the sense, in an algorithmic sense, that is not easy in computational sense, that is not polynomial, unfortunately, because the exponential step in determinization and equivalence only works, and minimization only works for deterministic equivalence, not that please. And actually checking equivalence of two regular expressions is polynomial space complete, so its complexity is high. It's not, but it's easy in the sense that it can be done. It's solvable. It's recursive language. But for the next level of formal languages, context-free languages that are given by grammars, then almost all algorithmic properties are non-recursive, cannot be solved by algorithms. In some sense, our today's class, the first of the two, we have discussed almost all algorithms of analyzing formal languages that exist. Because most of other problems for more complicated structures, like again context-free grammars or more difficult concepts of automations, they're unsolvable anyway, so we couldn't learn algorithms there. Now talking how to fix this algorithm to run in logarithm n. The problem is that we are detecting non-equivalent states, and if, for example, our automaton is already minimum, then it definitely cannot be improved to run faster than n squared, because all non-equal states are non-equivalent. What you could do is to look for look in the other direction. Let's start with the two equivalence classes, terminal and non-terminal, and split them. This is the opposite to what we did now. We kind of found non-equivalent one by one, but let's split, make mass split. For example, let's take this class T. Let's consider some character C and all edges from this class, all transitions from this class by C. If they all lead to non-terminal, for example, then we cannot do nothing new. We cannot do anything new because if we can differentiate between T and not T, this C doesn't help us to differentiate inside. But if some transitions lead inside of T, and some others lead outside, then we can split the class T. We know that these states and these states are not equivalent. So we can split the class T. And now we have smaller classes, so we can ask about them. So if you implement it like this, so you have this class, you put this again into the queue, you take the class out of the queue, look for all outgoing edges. If there are some edges, it ranges to different classes, then you split it and put the results into the queue. This time, since every time you split the class, the number of classes increases, and it cannot exceed n. So there are at most n pops and pushes to the queue this time. However, you need to consider all this transition, and there are at most n of them, so it's still n squared. So actually, the trick that goes to logarithm n is approximately the following. So if you have like a and if you have the class A and you split it to B and C, then for those classes, if there are classes such that all transitions came to B, came to A, or all transitions were out of them, so those classes that could not be already split by A. So either all transitions into A, or all transitions out of A. The classes with all transitions out of A, the situation for them didn't change at all. And for them, for those with all transitions into A, B and C have the same effect for them. Either all transitions for them go to B, or all transitions for them go to C, or some to B, some to C. In this sense, some to B, some not to B, or some to C, some not to C. So we can only put the smaller of these classes, in some sense, to the queue again. Not both of them, but only the smaller one. So this is the direction of the optimization, and after that, with appropriate organization of data of this incoming transition and appropriate definition of smaller, you can, like in other similar algorithms, every time you split a class, only the smaller part goes into the queue, so you can work with any class at most logarithm n times, so it goes to the logarithm in some sense. This is the direction. If you want to read about this algorithm, it's called Hopcraft. So you can get into more details. Okay, at this point I think we need a coffee break, and after the coffee break, please get back, and we will see the other side of automatons. This was automatons by themselves. In the next part, there will be automatons for people, for strings actually. And it can be also used in product again. So like for non-monotonic Boolean functions like XOR. So you can say accepted by this but not by this. So you mark the corresponding states. Okay. And this can be like in a general setup for Boolean functions, like we make a product of just one. This but does it work for NFAs to make the complement? The answer, the correct answer is no, because let's look here. For example, we want to this one except that are not terminated by AB, the hand with AB, yeah? Let's try. Let's make this state non-terminal and these other states terminal. Would it now accept strings that are not terminated with AB and B? He would accept them, but he would also accept all other strings as well, because this first state became terminal. This is actually the very fundamental principle of we have exists path from S to terminal. The negation of this is all paths from S lead to non-terminal, not exists path from M to non-terminal. But if we switch the states like this, we actually say exists path from S to non-terminal. There was a question in the break, what is T with the overline? That is the complement, all the others. So exists path from S to non-terminal is not the same as all paths from S to non-terminal. So this method doesn't, unfortunately, work for non-deterministic automatons. We'll get our automaton back because we will need it now. So, summarizing, we can get any Boolean function, including those ones with only one argument, like there is only one non-trivial such function, not, yeah? Which can be implemented. Okay, and for example, this can be used for also in the equivalence matching, like when you compare two sets of strings defined by regular expressions or by DFAs, or we ask like subset, for example, no subset for A. If I want, for example, some like A XOR B is equal to C. How do we check that? Make A XOR B using the product construction, and we use the not idea, yeah? So we can, if we use non-deterministic or deterministic automatons, it's okay, we can make so. So here it's very important. So if you have monotonic Boolean function, the one that doesn't use not, you can use non-deterministic automatons in your product. If you are using non-monotonic Boolean function, which is not, unfortunately, only deterministic. Okay, now as I promised, let's move on.
Yes. Like for example, in that case, like you have a DFA and an NFA.
If you have an NFA, this would not work. You need to determine them before.
Yeah, but
you cannot easily create NFA for XOR of them.
like,
but you can, for example, for intersection, because intersection is monotonic. You make a product and mark like L. You don't need inversion.
Can you negate only the DFA and that's an implication?
I think you can negate only DFA, but XOR you need to negate both. If you have some monotonic and some arguments, other yes. You have some representation that only negates the determinism. In the, well, very unusual case that you have some languages are given by deterministic and some by not, and you have such condition that you shouldn't get the deterministic part. I can't imagine the real life problem with that, but probably there are real life problems for anything for this as well. Okay, now let's move on. Our second part will be dedicated to discussing string algorithms using automatons. And the first algorithm that we're going to discuss will be the Morris-Pratt algorithm from the automaton point of view. We will start by reminding the prefix function, but to be sure that reminding is reminding, not only from scratch. Who knows prefix function? Please raise your hand. Well, 85%, not bad, not terrible. Not terrible. Okay, I will. For those of you who don't know prefix function, first of all, you might consider actually conducting, talking to your maybe coach, talking with organizers about moving to the Brazilian class, especially for Brazilian, I don't know, because it would be more useful maybe for you, because the topics are similar. For example, yesterday's topics in the class was also data structures, but they're from the more fundamental things. What we are discussing is advanced things based on some fundamental things. And if you don't know fundamental things, you're just having the gap that will be difficult to close later, because you will have the mixture in your head. So it's up to you. Of course, we are not asking anyone to leave, but you might consider what would be more useful for you. Now, I will now remind / tell you about prefix functions. This is not the best way to tell it for the first time. So those who listen to this for the first time, maybe you should read like root courses or whatever other source after that again to get a more fundamental description. So what is it? Let's say we will now talk about the problem of which is one of the most basic problems in the string theory, but it has very many different variations actually. It is pattern automation. Pattern automation, and we will talk about the simple setup where both pattern and the text are given as plain strings. It is sometimes called fat string search. The overview is the following. You can, first of all, you have several, two sides of this problem. One side is pattern. Pattern is the string that you are looking as a substring. And the other side is text. Text is the string that you are looking, in which you are looking for the pattern. Yeah? So the setup is defined by the following options. First of all, there can be one pattern. I will denote it as 1p, one pattern. Or multiple patterns. I will denote it as empty, multiple. Similarly, there can be one text. If you have only one text that you need to search in, it might look strange when the algorithm might have many texts, but actually it is quite useful. For example, the main boost of string algorithm, there were two of those. One was initiated by search engines in the internet, and the other was initiated by bioinformatics, actually by DNA analysis and others, like sequence analysis from natural sources. So if you have DNA analysis, you have one text, the DNA of, I don't know, some of your favorite bacteria, or maybe that you don't have human, and you want to do something with that. Or multiple texts. And the other option is the order. What do you have, like first and second? You might have like one text, multiple patterns. You have one text first, you can do whatever you like with that, and then you have multiple patterns, and the optimization point here is how fast you can process pattern. Or you can have multiple patterns, one text, which looks almost the same, but now you initially have patterns, and then you can, after you process your patterns, you have text. So these two setups are different, and you will see today, where I will consider most the setups, that they have different approaches actually, although both of them are automaton based. For the most basic setup, like one text, one pattern, or one pattern, one text, when there is one text and one pattern, it doesn't so much matter in which order they are given, so it's like more or less equivalent to one pattern, one text. There are actually two well-known approaches, I guess most of you might know. The first one is prefix function, which I will denote as KMP. The second one is known in the programming contest community as Z function, or it is, and more correct to say that it's an adaptation of so-called Maneker algorithm. The Maneker algorithm was initially developed for palindrome matching, for finding the longest palindrome, but it can be modified to be used for the pattern matching problem, and it has the jargon name Z function. The less known to the Olympiad community, but more advanced algorithms are, for example, Boyer-Moore algorithm, which had the advantage that for real-life data, when not specially constructed against the algorithm, it matches faster than the input size. So if you have random access to your input, so you don't need to read it character by character, you can match faster. The main idea is that if you, for example, in some sense, if you match from the end of the pattern, not from the beginning necessarily, from the end, and sometimes for some mismatches that you find, you can deduce that you can skip all the like this. So you do this, you match like this, and you find some mismatch that gives you so much information that you next time you try this pattern, and this can lead to like text length divided by pattern length. In the worst, it's the naive realization gives this in the best case, but this in the worst case. But you can make advanced realization which has this in the best case and this in the worst case. So, it's actually the thing. So-called forgotten algorithm. It was very popular in the previous century, and now it is almost forgotten. Does anybody of you know Boyer-Moore algorithm? Heard about that from the teacher? No, forgotten now. So you might, if you want to, if you want to revive it, you can look for it. It's Boyer. Very fast in practice for real life data. Actually, if you, for some unknown reason, are writing some, I don't know, editor, text editor, and they want to look for a pattern, if you use this algorithm, you will like lightning fast search. Okay, now for the if the order matters, we have these two main setups. Actually, one text multiple pattern is the classical setup for both suffix data structure. There are three most best known suffix data structures. There are suffix array, suffix tree, and suffix automaton. We will, since we are talking about automata today, we will consider automaton today. But it has advantages and disadvantages. The main of its advantages is that it has short code, it's very fast, it can do almost anything or other algorithms. Disadvantage is that this code is kind of cryptic, so if you don't, fortunately now you can have your team notebook for the code. I don't know, Latin America allows team notebooks? Yes. And but don't have the bucket please, because one of my teams this very year had the bug in its suffix automaton algorithm. They fortunately have found it out on the camp. We had also camps in Northern Eurasia, and one of the contests of one of the camps, they had like minus 55 in the program because they were looking for an error anywhere except the standard algorithm that they copied from the notebook, which was the one that was set. Okay, so suffix, and another disadvantage is that unlike tree, automaton will be a dot directly to cyclic graph. It doesn't have LCA. So trees have LCA in this common system. The ducks also have LCA, but no easy algorithm to find. For that reason, some automaton doesn't replace everything. But it is very multi-pattern pattern, multiple text. Actually, the algorithm that we will discuss today can also solve multiple patterns. Multiple text actually, the second parameter is usually multiple, because if you preprocess, then you can use the result of the preprocessing multiple times. Is the other classical algorithm that we will see today again, after course algorithm. That is a multiple pattern matching algorithm. Again, this algorithm can be seen from different points of view. We will look at this from the point of view of automata. Okay, not wasting any more time, let's get on with it. So prefix function. What is the idea? Let's take this let's take a look at them. So the problem that we will be solving is one pattern, one text. So we are given a pattern in the text, and we want to find all occurrences of this pattern as a substring in this text. So what can we do? So we have text. Let's put the pattern here. Text. Let's match characters one by one from the left to the right. So equal, 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 not equal. So here we have A, here we have B. So what is the idea? It is the naive algorithm that is, by the way, implemented in your favorite programming language, whichever it is. If it's not exotic, so it's C++, Java, and Python. All three implement naive algorithm for such a question. The naive algorithm does the following. It moves the pattern by one character and starts matching again. This one, this one, this one. But look more closely. We have already seen this in this example of two characters. And we know our pattern. Maybe we know that shifting it by one doesn't ever match, because if we shift it by one, there is no reason to match again because, for example, if pattern starts with A, B, no reason to shift it by 1. A will definitely not be equal to B. It was equal here, so we know that in text it will be the same as in pattern. So what is this called? The safe shift heuristic. It turned out not to be a heuristic in the end, but a real speed up. But initially it was called safe shift heuristic. So Knud, Morris, and Prats actually they found out that it was not a heuristic independent, and that it results in so okay. And suppose that you have matched correctly I characters, and the next character doesn't match. What is the reasonable shift for the pattern? You want this character, this new character of the pattern, say J character, to match the last J characters of the first I characters of the pattern, because they initially matched with the text, correct? So what J can we safely choose? We can safely choose the maximum possible J. So let's say that J must be maximum value. No, let J be the parameter. Maximum J such that pattern from 0 to J minus 1 is equal to pattern from I minus J to I minus 1. You can put the 0 index as we usually. So this value is called the prefix function. Another thing that we need to say that J is smaller than I, because if it's equal to I, it definitely works, and it's definitely maximal possible. So this is called prefix function, as you know. Now I need to be sure that I don't make any stupid. It is called the prefix function for I minus 1. Yes, because it's indexed 0, 1, so it's I minus 1. You can make I here anyway. Unfortunately, there is no way to get rid of all minus 1s. Here or there, they will happen. So just you need to be sure of where. So I will. For me, it's convenient to put it to the index of the last match. So, okay. So now, how do we? First, what is the benefit of this? Suppose that you know this prefix function. Then, after the first known match, you can shift the pattern like this, and do not try to match these characters again, because you're absolutely sure they will match. So now you can continue to try and match it from this point, and this immediately gives you a linear time matching algorithm, because you have every operation either moves the matching position to the right, or you are moving your pattern to the right. So both of this can only occur n times. But how do we know prefix function? How can we learn prefix function? How can we find this maximum? Okay, let's try. Suppose, well, P for 0 is actually definitely 0, because the only value less than 1 is 0. It is by 1 difference, so if we can make it for this to be easier. Okay, so And then we can replace I minus 1 with I. This. So, P of 0 is definitely 0. So now, how can we calculate value of P 5 for greater values? So let's see. So we have 5 for I minus 1. And this is like G. Now we are adding character number I. And what would it be added to this? That depends on this character. If it matches that, then we can increase by 1, and we definitely cannot increase by more than 1, because to the other side, increasing by 1 always works. If you cut this and cut this, it still matches. So it not increase by more than 1. Okay, so if this matches, okay, we are done. But what if it doesn't match? What is the next value that we should try? Well, the answer is we would suppose that this would be the answer. Then this matches this, and also it matches the beginning. So we clearly say that this is exactly the next variable that we should try is the prefix function for the prefix of length j, which is 5 for j minus 1. So this gives us the following kind of cryptic code for prefix functions. I of 0, 0 for I from 1 to n minus 1. We start with the value of the previous, so we have like j, yeah? So j is 5 I minus 1, while our part term with the index j is not equal to the part of the index I. J is 5 j minus 1. What if it never matches? So that it goes down, down, and down, becomes 0, and still doesn't match. So even one character doesn't match here. So we should give the answer to 0. So n 0 greater like this. And then, after this while, we say if phi p j is equal to py j plus plus py is equal to. So if match was found, we increase it by 1. That, for example, for the red one, if the match was immediate, increase by 1. If the match wasn't found on the first step, we go to the blue ones, and if the match is found, this one now with this one, then we go with the blue one plus 1. If the match is not found, replace in your head blue with red, and again go to the next blue, and so on, until the match is found, or until we collapse to the prefix of length 0, and still the match is not found, then we keep 0. Okay, so this is the code, and if you look at it closely, you see that this line is redundant because j is equal again to the result of the previous iteration. So you can remove this string with some small optimization, making it even more real. And it also works in linear time, although it has the while inside, because if you look at the value of j, it increases at most m times, and since j is less or equal to the argument of pi, and here we have pi of j minus 1, so j decreases here, it cannot decrease more times than it increases. When I tell this story to the 8th grade students from high school, I tell them you have a box of candies and you add the candies 10 times, how many times can you take the candy out? Yes, they don't know what I know this, like you know. Okay, so here we have a linear time algorithm for calculating perfect function, and then we already know how to use it, but it actually turned out that it can be that initial idea that led us to prefix function can be simplified then for the problem one pattern, one text in the following way. Instead of all this, say shift heuristic, which we'll get back to, we can use the following idea. Put the pattern, then some separating character like a sharp, and then the text. And using this algorithm, calculate the prefix function for the resultant string instead of just the pattern and then say shift heuristic. And then whenever the prefix that matches with the suffix is so long that it has the length of the pattern, at this point you have the occurrence of pattern matching. So as you see, the idea goes on that first we look at this, find the safe shift heuristic that gives us the idea that we should calculate this. We learn how to calculate this quickly, and then we look at what we have calculated and find out that we can drop our initial ideas and make a simpler solution. And that is actually the way you should also do it for the contest sometimes. When you come up with some complicated solution, after making initial preparations, you might use your calculated data to have a solution. That's good. That's a good story at this point. But let's get back to this initial thing, and let's do the following. Suppose that you have this parent, this text, and let's look at how this algorithm goes after this sharp character that separates the pattern from the text. So here we are, and we start from 0 because sharp character should be selected the way that it doesn't appear in either pattern nor text. So here we have j equal to 0 in this algorithm, and let's run this algorithm on. What goes on? Let's take a look at this part. What does it depend on? Let's see. First of all, it says pi. Now, since we have modified our algorithm, and now not only we're looking at p, but at p sharp t, let's replace it with x. Okay? So since this is now s, j will never be more than pattern length, because this sharp character prevents us from being that, prevents the value of j from being that big. So here we can keep pj, but instead of pi we write now si, because p doesn't have so many characters. Okay, so si is some character, call it c. Here again, psi, and it is c. So this blue box now, if we already know the value of pi for the pattern, we will never need actually the values of pi for such big numbers that are in the text part of the concatenated string. So we can drop this if we already know the pi. So this black box, actually what does it do? It takes j as input and gives the new value of j as output. So we can make it isolated as a function. Okay, it's isolated as a function like this. So this blue box is next. What does it take? It takes initial value of j and the value c of which is the next character that we are now considering as I. C. And this box here, should we have the electronic word, I will just move it there. Fortunately or unfortunately we don't have it, so you must memorize that. And we put a simpler text here like J is next J I. And I probably here is from m plus 1 to m plus 1. Because pi is already known, we have decided. We have calculated pi for the pattern only, and now we only have text. Or not pi, pg. Not g, s. We can move from to actually si with I from m plus 1 to m plus n. This part is actually only text character. We can replace it with text, but then we must move a little bit our indices, like just from 0 to n minus 1. Yes? Okay, and if j is equal to m, the length of the pattern, then whatever we need to do when I find something. Okay. What does it remind to us? The answer is it reminds us how deterministic the finite automatons work actually. J is kind of the state, and we take the next character of our input string. We look where do we go with that character from the current state and go there. And if we are in the terminal state, then we have found something. This automaton that corresponds to prefix function is called prefix function automaton, or alternatively KMP Morris automaton. Let's see how it looks. Actually, connecting different worlds, it's exactly the greedy determinization. Greedy, I mean the BFS determinization, the determinization that only keeps the reach of states of this automaton, of this kind. So, we have prefix function, and we build the automaton like this. So let's do this for this particular string AB. So I have the initial state. Well, J can be from 0 to the length of a string, in our case 4. So we have 4 states. 4 states. And the transitions are like this. So if we look here in the blue box, that we remember, we start from J, we look if the next character is the same as in pattern. Now pattern is, I remind you, AB, AB. If the next character is the same as in pattern, J increases. Okay, increases, nice. AB, A, B. If it's not the same, remember, we go to the state P of J minus 1. Yeah, so J is the number of the state. So where do we go? We go from J to P of J minus 1. This, and from there we try again matching. Let's look at the blue box again. We will now fix it a little bit. So next, JC, while pattern with index j is not equal to c, and j is greater than 0, j is pi of j minus 1, if p of j is equal to c, j plus plus, return j. Let's refactor this from while to recursion. Let's see, we make one step, and if it's not successful, then we're in the same state, not state, in the same, I don't know, snapshot of our function, but with a new value of j. That can be replaced with recursion. You usually, I don't know, in your programming techniques classes, you are sometimes taught the reverse. When you have tail recursion, you make it a cycle. We will do the opposite. We have the cycle, we will basically do recursion. So, if j is greater than 0 and p of j not equal to c, return next p of j minus 1, pi of j minus 1 of j, c. Else, if j is equal to pi, p of j is equal to c, return j plus 1. And the final situation is that this is not, it didn't happen, so j equal to 1, or this equals to this. It doesn't equal to this, so j must be 0. So return 0. Okay, so we have already drawn this. Now let's draw this. It's equal. If we are in 0 and the character is wrong, we just stay where we are. And now the final part is this. So if it's not this and not this, so if it is, we are in the 1 to 4th character, but the character doesn't match, we should go to pi of j minus 1 and then use the transition from there. How can we do that? Well, the pi of j minus 1 in the context of automaton, we will rename it and say that it's a suffix link for the vertex j. That is just the renaming. That is not the new entity. This is just the renaming of prefix function for the context of automatons. Because this minus 1, we didn't like it from the very beginning. You know? So now, let's see. It's easy. Now, first I will draw this. I will draw this suffix length as if I knew the prefix function. The next step will be to incorporate their calculation in our automaton calculation without previously creating prefix function using separate calculus. But for the first step, let's imagine that we know prefix function. Then it is like this. It is like this. From here, ABA, what is the maximum suffix that is equal to prefix A? ABAB, then the maximum prefix that is equal to the suffix AB. So this is the prefix function visualized as suffix lengths. And now we can easily create other transitions. So for here and for B we know it is this case. For A we should go by the prefix function and by A. That's the same. Now that we have renamed pi to sub, we say sub j. Okay? So we go by a suffix link and by A, get A. Then here for A we go forward, for B we go by suffix link and by B. So no chance we go there. Here by B we go forward, by A we go by suffix link and by A, and that is strange. Yeah? Because A, B, A, we don't go here, we should go here. What is wrong? Because we shouldn't go there. We should go where? We should go here, yes? Correct. Picture and nobody told me. Are you sleeping again? Please don't sleep.
Isn't it the same for the fourth node?
For this one, no. It's okay. A, B, it's okay.
So if you okay.
So again, let's look. A, here. Here, for we don't have both, neither A nor B. A, suffix A here, and that is correct because you see A, B, A again, so A, B again in the end. And for B, suffix and B, and that is a failure, complete failure. If we get B there, no chance to continue, we must start from scratch. So, if anybody would like to take risk and determinize this automaton by the subset bit mask algorithm, yeah, I claim that you would get the same thing without those blue lines, of course, but you would get the same. You can try, or maybe look on the internet for some determinizer. So this is the initial state, and talking about the terminal state. Well, okay, you don't want to accept anything. This is now just the found thing. Let's put the found thing to as the terminal state. So every time we pass through the terminal state, it's our found. That means that the currently read text ends with our button, and that is what we put here. Okay, so this is prefix function of K and P. Now about the blue links, the suffix links. It is a little bit inconvenient that we need to have a separate algorithm for prefix function, which being honest does absolutely the same that we do. Let's remind how the algorithm for prefix function works. Let's get back to that. We have M here from 1 next to Ti. Yeah, that's correct. That is not new. And we say P of I as J. So in terms of our automaton, we are starting. What is the initial value for J? The initial value of J is the prefix function for the previous position, which is the suffix link for the previous position. And what we do, so for example, we want to calculate let's calculate the blue arrows using this algorithm. So for 1, we have no option. Suffix link for 1 is by definition the prefix function for 0, which is always 0. For 2, we already run the algorithm. We take the previous, follow it, which is we go from J from the previous step, that is here, yes, and follow the Ti, which is the character which leads into our vertex along the path of the whole string, B. So we take this and B. For 3, we take this, and the incoming character is A and A. For this, we take this and B. So actually we get the following refactoring of this algorithm that calculates both transitions and suffix names. We go from well, zeros vertex is processed separately. All non-existent lists from it go back to it. So for I from 0 to n, if or C, we'll see whatever we have, C, whatever characters we have. If C is equal to the next character of a power, then go from I by C is equal to I plus 1. Go to the next and to M by the way. So here I minus M. C. Okay, next. If but okay, first let's put the blue arrow. So from 0 to M. If I is no 0, there is no suffix in because it would correspond to pi minus 1, which does not exist. There is nowhere to go from 0. We cannot go back anywhere, no back. So we don't do anything else if I is equal to 1. Then suffix length for I is 0 always, else suffix length for I is go from suffix length for I minus 1 by the character that goes to this vertex, which is pi minus 1. And next we do this. So if it's next, okay, else if I is 0, we don't have a suffix net, but we have nowhere to go anyway. So go IC 0 and else go IC is we go by the suffix length and then by the required character. Go by suffix I. So this is the complete, more or less correct, I don't know. You know the idea, but of course plus minus 1 since I showed you it's not dangerous. I think I did everything correctly, but you can never be absolutely sure with the algorithm that rely on minus 1s. You know that, I believe. So we have this algorithm for constructing this automata. It runs in linear time, unlike classical prefix function algorithm. It doesn't even have any amortization, any candies from the box. It's just for, and inside of that, this for C. It has its advantages. It's real time all time, but you can never have no disadvantages. Two disadvantages. First disadvantage. It has well, memory and time is multiplied by the number of characters. That is the first disadvantage. And the second disadvantage, well, it's way more difficult than the prefix function algorithm. There we have like 4 short lines. Here we have like maybe 15 lines. Right. Of course, if you don't need what follows, if you don't need its specific properties, its automaton representation, then no need to do this, just do prefix function, that function. Now, what are the benefits of automaton representation? Automaton is graph. You can analyze this graph using algorithms, just as we did with other problems on automatons. For example, the question, how many strings contain our given string as a part? Would be this would be difficult for us to calculate from scratch because there are overlapping patterns and inclusion clear. But with this method, what is the string containing pattern? The string that passes through the terminal vertex. Since after it passes the terminal vertex, it's already okay, we can fix this a little bit by directing the edges here like this and removing this. And now it's exactly the number of strings that we know well. It's like Bellman-Ford, similar to Bellman-Ford algorithm on the graph. Number of paths from S to T. Number of strings not contained in pattern is the same thing, all the same. You again avoid going through the terminal state, and so you can like remove this edge and calculate the number of paths of length L. And so on. So analyzing this graph, you can also, since it's automaton, you can now apply all that we have learned in the previous part of the lecture, like multiplying this automaton by another. For example, the number of strings that contain the given string as a pattern and contain the number of A's that is a multiple of 3. Sounds horrible, but now it just constructs from the bricks that we have learned in a direct way. And similar. So since I have this automaton, you can use all the algorithms on automatons that we have learned in the first part of the lecture by analyzing the so-called string combinatorics. So, I see the question? Yeah.
I don't understand the third line.
Which one? This?
Yes.
Let's see. If you remember the code of the prefix function, we have g from the previous, as it is the suffix of I minus 1. It is the g for the previous. So what you do, you run the blue box for the previous value of g to get the new value of g. What is the blue box? It is next from this to this. We just save those values on next in our two-dimensional array go. That's exactly what we do. Okay, now we are quite short of time. Let's try to do the following then. Let's generalize this algorithm to multiple patterns to get so-called autocorrelacy algorithm. Get out. How can we do this? We will need an additional data structure for strings. That is called a trie. The word trie was invented by Donald Knuth, and this is the word that is similar to the word tree because it looks approximately like the tree, and it could even be read as tree in some languages. And it is also a substring of the word retrieval, which is associated with a science. In Russian language, I know that nobody actually knows that, but the translators of the Knuth book had to invent something, and so they called the structure board, which is like the small forest in Russia, and it's the substring of the word board, which is like a selection. The translators, I don't know whether Spanish or Portuguese. How do you call this structure in Spanish? You see, the Russian translators were a little bit more creative. Okay. So the trie is the tree that contains the set of strings. How does it work? We have the root vertex, and we have, like in the automaton, suppose that you want to make the finite deterministic finite automaton for the finite set of strings, for the given set of strings. What could you do? You could just greedily, without any optimization, add all of these strings one by one like this. So for example, A, B, A, B, A, B, 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 A, B, A, B. Suppose you have this string. So you add A, B, A, B. And this is the terminal vertex because you must have this. And then A, B. A already this, B already this. You come here, and this is also a terminal vertex. You can also mark those terminal vertices by the exact which string. 1, 2, 3, 4, 5. So this is string number 1. This is string number 2. Now B. We don't have B transition from the root yet, so we get B. And this is the third string that terminates here. Then BA. B exists, A does not exist yet, so we add A. And the fourth string terminates here, and BAB similarly we add this, and this is the trie for this set of strings. So each, you can, by the way, think about the problem of creating the minimal by the number of vertices automaton for the given finite set of strings. Of course, you can use the general minimization algorithm, but there is a faster and simpler algorithm for this particular problem. You can think of that in your free time if you have any. But now getting back, so this is called the trie. You can easily add the string to a trie, just like we did, and you can search for the string in the trie by going from the root along the edges marked by the correspondence, just like you do in the finite automaton, with the exception that there are no cycles here, like it's a tree structure. So what am I going to do? How does the trie for a one string look like? Very easy. Just like the path in our KMP automaton from the left to the right, without all other stuff that we have added here, yes? So, what are we gonna do? We're gonna convert our trie for the set of strings to the automaton with the same functionality that the KMP automaton has. So that when it passes through these terminal vertices, that means that we have found the occurrence of the correspondence. The idea is the same, it's just the generalization from the bamboo to the general tree. So let's generalize the concept of suffix link. What was the suffix link? It was born from prefix function, but now we can say that it has its own meaning. When we go from this chart to some vertex, its suffix link leads to the vertex that corresponds to the maximal suffix that matches the prefix. The generalization for the trie would be that the maximal suffix that matches not necessarily the prefix of the same string, but the prefix of some strings, because the strings can be mixed in the text. So in this case, the prefix of any string in the trie is just the vertex of the trie. So the suffix link in the trie, the suffix link in the trie is the maximum suffix of u in the maximum v, maximum depth v not equal to u, that, well, I will denote as v in brackets as the string that goes to v. is the suffix of the string that goes to you. Let's make some of this by hand. For example, here, ABA. Do we have BA in the try? The largest suffix not equal. Yes, so this would go. AB again. Do we have BAB in the try? Yes, BAB. So it goes here. It's like a regular try. Let's add something like ABBA. Number 6 AB. Number 6. So for this vertex ABBA, BBA we don't have in the try BBA. So BA we do have, so this would go there. And doing this, we can actually generalize, making this, we can actually generalize this algorithm with the only exception. Let's do that. So for I from 0 to m doesn't work anymore because we don't have one string that we can iterate. For multiple, we will need to iterate in some order. We will discuss it in a moment. So if I equal to, so this is set up for we, or for u. If u is root, then we don't have the suffix. Look again, for this definition, there is no suffix of the empty string that is not equal. So else, I equal to 1, what did it mean? It meant that this is the first vertex, and the only option was the root. Now, if this is the child of the root, so if parent of the u is the root, for the same we can tell that the depth of the u is 1, or make some other observations, then suffix length for u is root. Else, the same algorithm actually works, but -1 doesn't work again because the numeration is not global. So what is the equivalent of -1 for the tree? Parent. Yes. So we go like suffix for the parent of vertex u, and what is the character? What was this pi? What was this p I -1? That was the character that led from -1 to I. In our case, that will be the character that is written on the edge that is going into our node. Let's store it in, for example, in. So this is the character on this edge. Now, this c equal to py, and I less than m. That is actually, we were building this path to the right. When we were working with a set of strings, it would be easier for us to build the trie separately and start with the trie. So this part means that this edge already exists in the trie. In this case, we don't touch it. So if, say, go from u by c is not equal to some -1, then must is quite what people say. We don't touch the edges of the trie, they stay. In the other case, again, if I equal to 0, that is equivalent to be in the root. And this line surprisingly stays as it is, except that. Okay, so this is the setup for the vertex. converted from the setup from the vertex in the one string element. Now the two remaining questions that we have. First is, in which order should we set up our group? BFS. You see, there are actually two options. I like one of them. My friends, for some unknown reason, like that. I like BFS, right, for search, going down layer by layer. Why does it work? Because we are referencing to go from suffix links. Suffix links always go up, so it's safe. They are already initialized, and the here suffix for the parent is also initialized, so they are completely safe. For some reason, some people don't like BFS. It is difficult. The algorithm which uses Q, it cannot be implemented using recursion. I don't know. You are laughing. That is true. In one of my colleagues, the teaching BFS is the least thing for the class. Right? For me, it's quite easy. But okay, those of you who, similar to my colleagues and some of my colleagues' students, are afraid of BFS and only like DFS. You can use DFS, but it is dangerous because, as you can see, those suffixes can go to completely opposite part of the tribe. So what you should do then, you should use kind of lazy initialization. So for each vertex you store if it's initialized or not. If it's not, before asking for its go, you check. If it's not initialized, you call initialize. If it's initialized, you don't. If you do this, make sure you know what you do. I recommend using BFS actually, really. Don't be afraid. Well, okay. Now, the second question is how to use it. So, after you convert it to the automaton, let's do it anyway, and we will go to lunch. Only a small automaton between ourselves and our lunch. So, for the root, no suffix. For the children of the root, suffix goes there. B exists, A, suffix next to A. So A exists, will be suffix link and B. Here, suffix link plus B. Here, and A and B both exist. Here, suffix link of the parent and A, suffix link goes here. B exists, A, here, and A. And so on. So you go down by the BFS and you initialize all the suffixes and transitions. The algorithm is quite simple. You just, and organizing the BFS, you can just inside the setup put the children of this. Like here, pass, not pass, but and here, go to senior. So this way, the BFS runs. Okay, so then how do we use it? Consider, suppose that we have finished that. We will imagine that all the missing links are there. So let's take some like A, B, A, B, A, B. Nice line. Let's start. A, B. Oh, I have found A, B. Great. A, B. We have found A, B, A, B. Great. A. We don't know. You don't know where A will go, but I will tell you. Definitely. So A, B. Oh, we have found another A, B, A, B. A, B, and another A, B. Looks good, but not correct, because there are a lot of other pattern occurrences in our string that we haven't found. Like B 4 times, BA 3 times, BAB 2 times horrible. The algorithm evidently doesn't work. How can we fix that? The truth is that when we come into some vertex, we have not only found the occurrence that corresponds to this vertex, but also to all suffixes of this vertex. Where are all these suffixes? How can we find them? Yes, we have suffix links that follow the suffixes. So, for example, here, we go here and also find B and B. Then we go there, I guess, and also find AB. And then we go there and also find B. So every time we actually hit this vertex, we also hit all this. So this is almost complete. So if we do this, we walk along our try, now converted to the automaton, corresponding to the string that we have. Every time we visit the vertex, we follow the suffix name, printing all the patterns that we match, and we have found all patterns in the time. Let's see. Time to build a string is the sum of the length of the strings. Time to walk is n. But time to match is now not easy to evaluate. It looks like something like the maximum length of the pattern times n, because every time I have to walk up to the very top. And there is example. For example, I have two patterns, A and A 100 times. Suppose I have two such patterns. In this case, how would the try and the automaton be? We have like this 100 suffix length go up one level. So suppose you have you are reading a single case. So and this, and actually it's not 5 but 100. So you are reading A, okay, then you are reading another A, walk up and match this A. You are reading another A and you walk up and at some point you match this A, and so on. So this is not optimal because our walk along suffix links make a lot of wasted operations. What would help us, and this is the final hero for today's lecture, is super suffix links. Our superhero. The super suffix link is the closest terminal vertex along suffix links. So for our super suffix links, for all vertices that lead to this one. If we follow super suffix links instead of just suffix links, we will make matches in the time proportional to the number. So that will be the sum of length of our patterns plus the length of the text plus the answer, the total number of occurrences. If the question is not to find all occurrences, but to find like the number of occurrences or the first occurrence of a string, it can be optimized out. Some not so difficult tricks to, like, in some sense, removing the terminal vertices or counting the number of terminal vertices that can be reached by suffix links. There are tricks, but let's solve the general problem. So how do we calculate super suffix links? Very easy. If terminal at from u is not, I don't know, -1, then super of u is equal to sum of u, and else super of u is equal to super of sum of u. Okay, if our suffix link is the terminal vertex, then that is exactly what we need. If it's not, then we skip it and go immediately to where x would lead us. So what I have constructed is the so-called automaton-based autoheuristic algorithm. We can get rid of it has a drawback that you need to store the automaton. The try generally is a little bit more compact than the automaton because the automaton keeps all transitions for all vertices, but the try only keeps required transitions. In a similar way to prefix function algorithm, compared to this automaton algorithm, you can remove this transition, only keep the suffix link, the analog of the prefix function for the try, and do the while thing with candies in the box like we did in the prefix function, but you need to be careful not to get quadratic time at build time. So, personally, if I write alpha-heuristic at the contest, I create the automaton version. I am not myself sure how to avoid this. So that's all the question.
Isn't it possible to store the number of terminal?
If you only need to count the number, yes, instead of the super link, you use count. So this count is count of sub plus one. In this case, it's count. The problem with the asterisk, the advanced program for those of you who know algorithm trees, the inverse problem. You need to count for each button how many times it occurs. Try to think about that during our absolutely wonderful lunch that we're going to right now. Thank you. Let me check if I have yes? Great. So I hope that not only that yesterday tutorial fixed, but the system of publishers tutorial fixed. So now you will have the